Just want to change your application, to teach it to raise its hand, to say, I'm here. If anybody needs me, I'm at this IP, this location, etc. So we've got on the class path here in my build, Spring Cloud Starter Eureka. This is the Eureka implementation of this Spring Cloud Discovery Client abstraction. So I'll say @enable discovery client. Whoops, wrong one. Command F9. And come on, computer, faster. Good, good. No. How is that blocking? I guess that, did it work? Oh yeah, it did work. Okay, so there it is. There's our reservation service at JLong MBP home reservation service. And if I go to reservations, could not prepare statement. Son of a. Oh, this is H2. We have ways to fix this. H2 got upset. That's why I was confused, because it restarted and it said it was preparing a statement or something like that. It was stuck on something to do with a database. I've got an embedded in-memory database. It didn't like my restart trick. No big deal. So there's that. It's registered in the registry. It's now available for consumption by another service, a client, and that's what we're going to do. We're going to build a client to talk to that service. We're going to build a client called the reservation client. It'll use the config client, Eureka support. It'll use Zipkin for distributed tracing. It'll use web support, REST repository support, actuator support, Zool, the microproxy, Hystrix, the circuit breaker, and I think maybe we should use Feign just to make it go faster. And then that'll be it. I think that'll be it. That's enough for now. Is that enough for now? It's probably enough for now. We could do OAuth. Just in case, maybe. Okay. And we'll hit go, open that up, comment out the bits we don't need just yet. So OAuth. Okay. And Zipkin, don't need that yet. And do I have RabbitMQ in here somewhere? Oh, fancy. Okay, good. So this is going to be a client that will talk to the registry just as before. It'll participate in service registration discovery. In order to do that, we need to give it a name. So what the spring.application.name equals reservation-client. Now, this is not just a client for the sake of building a client. We're building a special kind of service called an edge service. An edge service is just that. It's a service that lives at the logical edge of your architecture. It responds to requests from a field from your actual clients, your iPhones, your PlayStations, your Rokus, your Xboxes, your Teslas, your smart TVs, your whatever, right? Anything and everything these days has an IP address. There are streets in neighboring Singapore's roads that have IP addresses in them. They have sensors that feed into a grid that they use for traffic shaping. Human beings are walking around on the planet right now with organs connected to the internet, right? There are a lot of different clients out there, and these things are going to want to talk to your services. So instead of changing every single one of your services to accommodate each of these different kinds of clients, you should handle or adapt these things at the edge, at an edge service. The edge service is an ideal place to handle sort of cross-cutting concerns, things like security and rate limiting and routing and these kinds of things. So we're going to build a simple edge service. One common example is if you're building an HTML5 client. HTML5 clients are very powerful, right? I don't think this needs to be underscored too much these days in 2016, but how many of you have seen JS Linux? This was built by a guy named Fabrice Ballard, who in 2011, upon the introduction of typed integers in the JavaScript language, did the unspeakable. He wrote an x86 machine code emulator in JavaScript, because why not, right? So what this is, Wi-Fi permitting, is it's trying to download a Linux kernel. So if you could just stop torrenting for a second. Wait for it. We could leave it. It is coming from the other side of the planet at this point. Well, we'll leave it there, awkwardly. I want that to win. So anyway, the point is the HTML5 browser today is really, really powerful. You don't really need to hold its hand. You don't need to babysit it. You don't need to hold, to treat it like it's going to break. It can do amazing things. You can do 3D video games. You can do Linux, maybe. There you go. So let's just make sure we understand what just happened here. So I'm in a Linux command line. Like, people were excited recently when Windows was able to run Bash. Who cares? I was able to run Linux inside of a web browser 5 years ago. So here's a Linux shell. I'm going to open up my C code in VI, and I'll say escape, okay, hello, Melbourne, extra exclamation marks, escape, :WQ. And what I'm going to do is I'm going to do TCC. This is the tiny C compiler as opposed to GCC, which is available. I could use that. But when you're compiling C code on a Linux distribution running entirely inside of an HTML5 browser, performance matters. So, optimize that last mile at least. So here we go. I'm going to compile the code. There's no server-side state. This is all just running on inside of the browser. And I mention all of this as a brief digression for us to enjoy the ridiculousness of the situation and to appreciate that the browser is super powerful. You don't need to, like I said, it's not limited, but there is one restriction. It lives in a secure sandbox, a sandbox that precludes it from making requests to other hosts unless you add an access control header to that service, to the service to which it's trying to connect. So if I'm trying to call services A, B, and C, and they're on different IP addresses in my HTML5 client, I'm going to be restricted. I won't be able to call that service. I can add these access control headers to every single one of those services, but this would mean changing every single microservice just to accommodate one new client. I'd end up in a situation where I'm constantly redeploying all my services, which is what I want to avoid in the first place, right? So instead, proxy the request through something like an edge service. Serve your HTML5 assets, your JavaScript assets, your client in one node, and then have a proxy in that same host and port, and then proxy it. So that we can do that using Zuul. Right? Zuul is a micro proxy here. So I'm going to use Zuul. This is from Netflix, so I'm going to go ahead and start this up. Now, Zuul is obviously named for Zuul in Ghostbusters. This is Zuul. Or not. There it is. Come on. Now, I don't know if you've ever seen Ghostbusters. How many of you have seen the original Ghostbusters? Okay, so you know that Zuul is the gatekeeper, or the proxy to the underworld. Right? Or at least that's what I'm pretty sure. It's been a while since I've seen the movie, if I'm honest. And I had a friend who said, Josh, that's not fair. You can't assume he comes from the underworld. He might come from some really nice place, like Hawaii or something. Who knows? Whatever. Anyway, point is, that's him. And this is Netflix, and they do movies, so it's a movie reference for never mind. Anyway, moving on. So localhost, 99.99/reservation -service /reservation. So I'm making a request on the edge service at localhost 99.99, which is the node that I just created. I'm providing a context path that is the ID of the service that I want to call as it was registered in the registry. And then I provide the actual path. So what I have here is the edge service here, calling the downstream service, and I have the actual service here on port 8000. Right? So there's the actual service, edge service. Actual, edge. Actual, edge. Actual edge. Actual, edge. Actual edge. Actual, edge. Now, you may have noticed a few things different about their outputs. First of all, the URL is longer here. So the downstream service, the actual service, is seeing the incoming request that's being made by the microproxy, and it sees in the incoming requests headers that it can use to understand the origin of the request. And so it uses those headers to rewrite the URL so that from the perspective of the iPhone client or the HTML5 browser or whatever, it has no idea that JSON originated on any other node besides the node to which it connected. Great, we've got location transparency. The other thing you may be wondering is how does it know which node it should make the request, or to which node it should make the request? It does this by looking at the ID in the registry itself, in the URL, in the context path. That service ID is used, it then takes that service ID, it goes to the registry, it works in conjunction with Spring Cloud's discovery client abstraction, it calls the service registry, and it gets all the registered instances of that service in the registry, and it picks from among them, like a Pokemon. I choose you. That joke kills in some parts of the world. Why not here? Whatever. Anyway, it picks that instance based on some sort of programming logic that you provide, a load balancing strategy. It's an object that you can plug in. The default is round robin. But You can plug in whatever you want. You can do data center aware load balancing. You can do, I've got an OAuth token and I want to route to a stateful process where I'm streaming a video load balancing. I want to do data center aware load balancing. I want to do multi-tenancy or data sharding or data locality. All of these load balancing strategies, you write them, plug them in, and Spring Cloud will automatically employ it in routing to the right node here, all in the blink of an eye. I've only got one instance of that service registered in the registry right now, so yeah, it's using that one. But if I had 10 or 1,000, it would pick. So we get all that for free, and this may be enough. If you've got homogeneous HTTP-based JSON services, and you don't mind parsing and transforming all the data in the client, maybe you've done everything you need to. Maybe you're done. Sometimes, however, it's useful to be able to transform the downstream services, or to create or to synthesize a new endpoint, or to transform the data, or to derive a new view of the data from existing views. More than just blindly proxying the data back and forth, you're actually creating a new endpoint of some sort. This is a client adapter API, right? This is a very common thing to do. It's not something that all services are going to need. It's an endpoint that maybe just your iPhone client needs. Maybe you've got a watch that needs it's a bandwidth constrained. It doesn't need all that extra JSON, so you can save it the bandwidth costs, for example. Whatever that use case is. So in this case, what? 3 minutes? Until what?
Until 3 minutes.
Okay.
3 minutes till 9. Until 9.
Okay. Well. I don't even know how I could wrap it up here. Do we need to 3 minutes? Don't I get credit for starting a little late?
You can keep going.
Because it wouldn't. I mean, who wants to leave really badly? Who wants to leave? It's okay. I'm not judging you. I'm gonna just take it for, I won't cry. It's okay. It's online. If you want to go watch it. Okay, let's do this. So I'll go as fast as I can. Right now I've been going slow. I've been just leisurely going through this as slowly as I can. So what I've got now is I've got this proxy. I may want to create a new endpoint, a synthesized endpoint. In that case, I want to do more than just blindly proxy the data back and forth. So what I'm going to do is I'm going to create an adapter API, a very simple one, a nonsensically trivial one. I'll say class reservation API adapter REST controller. Okay, and I'm just going to make this a REST controller. And what I want to do is I want to create an endpoint that just returns the names, Josh and Trisha and Rashmi and Nasrin and Andrew and so on. Nothing else, not the surrounding JSON strata, just the names themselves. Okay, so, public collection of string names, return, and it's going to be a get endpoint. I'm going to map this REST controller to /reservations, request mapping. I'm going to map this endpoint to reservations /names, and I'm going to return just the names. And I need to actually derive those names. I want to call the downstream service, and so I could use Spring's REST template. The REST template is a convenient client-side object for calling HTTP services, and it would certainly work. I could create a load-balanced REST template like this. I could say @bean @load-balanced REST template, and then I could say return a new REST template, and that would actually be a smart REST template that would do the right thing if I said, for example, if I injected that REST template here, I could say that, okay, and I could say REST template.exchange HTTP reservation hyphen service /reservations, and that would actually get extracted and then load balanced in the same way that URL context path got extracted, right? That would work, but I would argue that this is a little low level, and if I had to do this kind of stuff for every single REST call, I think I'd spend a lot of time rewriting client-side code, HTTP code or messaging code or whatever. I don't want to have to waste too much time on that. So one question that a lot of organizations struggle with is who builds the client? If I have different services and I want other teams to consume that service, should my team, the one that built the service itself, build a client API for those other teams? A lot of organizations are worried about this because they worry that there's the risk of the service team building too much magic into the client, too much business logic that shouldn't be there. That client should be as thin as possible. A lot of organizations have different perspectives on this. Amazon says, no, you can't do that. Let some other team do it. That way it's a clean room sort of thing. If the client works, it works, but there's no magic that isn't in the business logic on the service itself. That's one way to do it. Netflix, I think, takes a sort of middle ground. They're very pragmatic. They have a nifty library called feign. Now, of course, as you know, in English, feign means to pretend or to act as. So if you are walking in the forest and you see an animal with its tongue hanging out like that, jittering maybe, it's scared. It wants you to leave it alone, so it's feigning death. It's feigning to be dead so that you'll leave it alone. It's not actually dead. It's fine. But it wants you to leave it alone, so it's feigning dead. It's very, in this way, it's just pretending to be or to act as, right? In the way that WebSphere feigns utility. It's not actually useful. It pretends to be useful, right? So what we want to do is we want to build a REST client without worrying too much about writing all the REST code. We still want REST, of course, because REST is HTTP, and HTTP is an amazing way to build services. So we're going to use feign. I've got feign on the class path here, I think. Feign. Very good. Okay. And I'm going to go here. I'm going to say @enable feign clients. Okay. And I will now build an interface, a declarative interface. I'll say reservation reader. And I'll say @feign client. And I'm going to tell it which service I want to call, reservation-service. And I'm going to provide a few definitions for endpoints. And I'm not going to worry about implementing them, right? I don't have to. So we'll say that this endpoint, when called, is going to be translated into an HTTP GET call that calls the reservations endpoint on a service that will be derived by doing load balancing. Now, one problem we have is that we don't have this type here, right? So I can create a type, get rid of that, and I just want a DTO, if you will. Now, a lot of organizations, they struggle with this as well. Where do you store the types that should be shared, or should they be shared at all, right? In this case, it's just one field, so I don't feel like I'm going to end the world or anything like that. But I would embrace things like schema if you can, right? Things like Google protocol buffers, which has some ancillary benefits as well. It's also more efficient than straight HTTP, right? So Google protocol buffers is very nice. I recommend that you check out this blog by one of my all-time favorite authors and blog authors on the topic. For your own reference and edification for later, okay? So there's this. Now, come on, friends, keep up. Anyway, moving on. So there's my simple REST interface, my REST client, rather. I can now inject this. I can say private final reservation reader. There we are. And now that becomes much simpler. I say read dot get the content stream dot map. I'm going to map it from a reservation to a reservation of reservation name. And of course, this is a method reference in waiting. And I can collect it into a list, right? Simple. So now, I've created a simple endpoint. Let's restart that. And that'll work. I mean, it should do the right thing. It'll give us the strings, the names in a JSON array without all the surrounding JSON strata. So let's see if that worked. Localhost 9, wait, what did we say? Somehow, client is on 99.99. For some reason, I forgot that. Localhost 99.99 reservations / names fail. What did I do? Context, but it's this endpoint. Wait a minute. I forgot to add dev tool, so my command F9 did 0. Absolutely nothing. Dev tools. Okay, next time. Scope runtime. Okay, there's this, and there's my names. So that worked. The happy path worked just fine. I called the downstream service. I got a collection of names back. But I've hand-waved a few real concerns here. First of all, what if I had more than 10 records or 8 records, right? If I had 1 million records, I wouldn't want to select all in this case, right? I want to stream the results. For this, I need something a little bit better. What about if I had more than one service to call at the same time? I don't want to call these things sequentially. I want to concurrently call them and then join the results up. For both of these use cases, the aforementioned reactive programming is a really, really worthwhile thing to look into, right? Reactor, the project Reactor at Pivotal is leading the way here. RxJava is definitely the original sort of 800-pound gorilla of the reactive space as well. The folks from Pivotal, Lightbend, nay, TypeSafe, Red Hat in Vertex, RxJava from Netflix. All these are different contributors and signatories of the Reactive Streams Manifesto, whose ideas then led to what she talked about earlier, the Java util concurrent flow stuff, right? In JDK 9, it's such a big common idea now, right? So for that, I would definitely check out that. We've also ignored one other problem. What happens if there is no service to respond? What if I call this service and there's 0 instances of the service in the service registry? It's going to try and load balance by 0, right? And that won't work. That's not going to end well. I mean, I'm sure we all know what happens if you try and divide by 0, right? What is 0 divided by 0?
Imagine that you have 0 cookies and you split them evenly among 0 friends. How many cookies does each person get? See, it doesn't make sense. And Cookie Monster is sad that there are no cookies. And you are sad that you have no friends.
So don't divide by 0. You'll make Cookie Monster sad. We can't load balance by 0 either, right? We need to understand that in a sufficiently distributed system, failure is an inevitability. It will happen. It's not a matter of if, it's a matter of when. High-performing organizations understand this fact intrinsically. Organizations like Google. There are people that wake up every day at Google. They get up, they put on their Google shoes and their Google underwear and their Google socks, put on their Google t-shirts, and then they get on the Google bus or the Google tram. They go to the Google headquarters where they talk to their Google colleagues, probably taking in the Google breakfast, the gourmet Google breakfast, while checking their Google Mail and their Google phones, drinking voluminous amounts of Google Kool-Aid, which is, what I would do. Sometimes, as is wont to happen, given the human condition, accidents will happen, and when they're drinking that voluminous amount of Google Kool-Aid, they may spill Google Kool-Aid on their Google shirts. That necessitates a trip to the Google laundromat, where they'll, of course, do their Google laundry. This may take an hour or two, but darn it, it's worth it. And in the interim, they'll walk around in the Google laundromat in their Google gold sequin bathrobes, waiting for the Google laundry to be finished. Then after that, they may decide to get back on that horse and go back to the Google cafeteria to have their Google lunch, because they've earned it. And after that, they may then decide, seeing as it is now getting on past 4 in the afternoon, to go back to work. And for some of these Googlers, they may get on a Google shuttle or a Google bicycle and go to the Google data centers, where they will stroll the Google data center aisles. And for some of them still, they will find completely and utterly unsurprising to them that some of their Google servers have Google died. You see, Google has more than 2 million production-grade servers deployed in data centers all around the world. 2 million servers, beefy servers, deployed in data centers all around the world. Statistically, something's going to die every day. They don't care. They didn't build their systems to be sensitive to the loss of a single node or even a few nodes. That's why they're Google. We need to do the same thing. We need to understand that failure will happen. Netflix also understands this fact intrinsically. They're zealous about it. They've got sort of a religious, fervor for building systems that are robust and tolerant to failure. They even have a suite of software components called the Simian Army. These are basically little agents of chaos that they loose in production systems during office hours when people are on hand, able to respond. The Simian Army are just little things that do terrible things in production. They kill -9 processes. They RMRF database and disk partitions. They block ports. They even have something called Chaos Kong, which even as I talk to you about it and pronounce the words now, gives me goosebumps. It purposely kills a whole data center availability zone. They do this to themselves during office hours to make sure that if it actually happens, their failover systems are going to work well. And if it doesn't work, then there are people on hand to respond. They'd much rather figure this out at 2 in the afternoon than at 4 in the morning when people are trying to sleep. They know that failure will happen. They have built their systems to be cloud native. We need to care for that use case. While this is going to be fine, in this case, the 80% case is well served here. If I have 1 or more instances of that service in the database or in the registry, everything's fine. But if I have 0, I'm going to try and load balance by 0, and I'll make Cookie Monster sad. We need to do better. One way to do that is just to ask the question. By using the discovery client, we can inject the discovery client and ask the registry, is that service there? But even if we don't do that, we should at least have some sort of graceful degradation. We should specify a timeout, first of all. But we should also provide a fallback mechanism, right? If something goes wrong, if we make the call and it doesn't work, we need to be a little bit more robust. So we can do this by introducing a circuit breaker. Okay, so I'm going to bring in the Hystrix circuit breaker that's on the class path here. And I'm going to build in a fallback mechanism. So I'll say public collection string fallback, return new array list. And I'm going to specify that if something should go wrong, that fallback method should be invoked. Okay? So Command F9. Did that work? I forgot to start it. Here we go. So what that's going to do is if there's an exception in trying to make that HTTP call, it's going to load balance, it's going to throw an exception, the Hystrix command is going to be invoked, the fallback method will be invoked, and the client will get an empty array list instead of a big fat giant Java stack trace, which is, from the perspective of an iPhone user, basically like an ASCII middle finger, right? You want to avoid that. So here's the happy path. I'm making the downstream service calls. Everything's fine, hunky-dory, no problem. Go back to my thing here, kill this, goodbye. Stutter, hesitate, empty array list. Stutter, hesitate, timeout, empty array list. Stutter, hesitate, empty array list. It's calling the downstream service, but if I wail on this enough, like this, there we go. Now, no matter how many times I hit it, it doesn't stutter anymore. You see, that circuit breaker is no mere try-catch handler. It's much more intelligent. It sees that enough successive attempts to call the downstream service have failed. So it opens the circuit. It switches the train tracks. It goes directly to the fallback. That gives our downstream service time to recover. We all know that if a website is responding slowly, the best thing you should do is to wail on the refresh button in the browser. Is that true? Of course not, right? Doesn't work for distributed systems either. So this protects against that effect. It gives your downstream service time to recover. If you have something like Cloud Foundry, which is a cloud platform, it'll automatically detect the failure of that node and restart it. It'll restart the service all day and all night until the cows come home. That means you can sleep easily knowing that the service will eventually recover. It'll wear the proverbial pager. But it's our job as developers to build services that do the right thing in the face of these, occasional service outages. Right? And that's what we've done here. We've given ourselves time to recover. That circuit breaker is also pretty smart, though. So if I restart this, it'll eventually re-register with a registry, and the circuit breaker will get a heartbeat event that'll tell it that the client-side perspective of the registry has been updated, so it'll invalidate its current cache, and then it'll see the new node, and it'll let traffic go through again. Right? It'll try and reintroduce traffic eventually. It'll heal itself. So we've built a system that does the right thing in the face of service outages and failures. Now, if we were trying to solve the write use case, this would be a little bit more nuanced, right? You can't use a circuit breaker for write, right? I mean, where are you going to, you still need to absorb and sort of record that write somewhere. And there's a lot of different patterns, a lot of different approaches, but I won't go into it now as we're sort of short on time. That said, you might look at CQRS, right? Great pattern, CQRS. Eventual consistency, that's a $5 word for messaging, right? Store and forward architecture. This is an idea that is 40 years old and growing, right, easily. You can look at the Saga pattern. This is an idea from the 80s. This describes a way of modeling a system that eventually converges upon a well-known correct state, even in the face of failure, if you can meet three constraints, which is to say that your transactions are either the unit of work that you're trying to get, to agreed upon is it has a rollback, a compensatory transaction. It has to be idempotent, and the transaction has to be interleavable, so I can do things in different orders. If you can meet those three constraints, you can achieve the Saga pattern. Whatever you do, whatever you choose, don't use distributed transactions. That is provably the worst way to solve this problem. If you're trying to get different distributed systems to agree upon a well-known state, the worst way to get that is to use distributed transactions, as represented on the Java platform by JTA. JTA is client-side middleware for the XOpen protocol, right? The JTA creates an unnecessary and dangerous single point of failure in your system, and it's also very slow. If you find you have the urge to use JTA or distributed transactions, I urge you to take a moment and stop and reconsider. Go home. Hug your significant other, pet the cat or the dog. Drink excessively, perhaps. Take vacation and reconsider your terrible, terrible life decisions. And then come back afresh, ready to go, and try anything else, because there are better ways. Anyway, digression. Once you've done that, once you've solved that problem, you might take a look at Spring Cloud Stream, which makes it dead simple to introduce messaging into a microservices architecture. If we had more time, we might talk about that. But for now, let's turn instead to these last two concerns. We've talked about building services that do the right thing in the face of service outages and topology changes. That's what the circuit breaker and that's what our service registry is giving us. We've looked at how to build apps that take advantage of the scale of a cloud-native system. We've looked at how to build a system quickly that's agile. And we talked a little bit about observability. We talked about the actuator, and the actuator makes it dead simple to observe the state of a particular service, one individual service. But what about the systemic perspective? What about the aggregate perspective, the bird's eye view of the whole system? Not individual services, but the system itself. You see, these services have emergent behavior that you can't appreciate by looking at individual services. If I walk around here in Melbourne, is that the same thing as looking at the Google map for Melbourne? Of course not, right? There's appreciably more happening on the ground here with the hustle and bustle of the people, seeing people all around, seeing these amazing buildings, clean, beautiful blue air. I mean, all the stuff you can't really appreciate by looking at the very two-dimensional map. The map is not the terrain. And the same is true of your production systems. Your architecture diagram is not the same as your production system. There's emergent behavior that you cannot hope to appreciate and to capture unless you're in production, monitoring the system itself and the interplay between those systems. So one example of that is that circuit breaker. That circuit breaker is a connective tissue. I can use it on code that connects from one node to another. I can't change other people's systems. I can't make them write code that isn't terrible. I can't make them use Spring Cloud and Cloud Foundry to build robust services that stay available. All I can do is protect my code and my systems from their terrible code, from their terrible services and their failures. That's the glass half full perspective, by the way. Right? So what I need to do is I need to be able to monitor those systems. I can't insert my monitoring infrastructure in somebody else's APIs and somebody else's code base. But I do need to be able to keep an eye on that because my code is dependent on that. So that circuit breaker is an ideal place to put that monitoring. If I monitor that circuit breaker and the circuit breaker says that that downstream service isn't working and it opens up, then I know effectively that that service isn't available. By monitoring the circuit breaker, I can monitor other services. It becomes a proxy, if you will, for that information. So let's do that. Let's build a service, a dashboard, to monitor that circuit breaker. I'll go back here. Oh, by the way, did that work? Let's see, localhost 9999. Come on. Reservation names. There's the service, by the way. I restarted the reservation service and it healed itself. So we're going to go back here. I'm going to build a dashboard for the circuit breaker. Hystrix dashboard. Config client, Eureka discovery, hit generate. Okay. Now, this is going to require, why do I always jump the gun on that? Here, Spring application, .name, Hystrix dashboard. Now, Hystrix is the name of the circuit breaker that we're using in our code. We'll say @enable, Hystrix dashboard, @enable, discovery client. Okay, and there we go. So that's going to spin up on port 8010, I think. And it's going to expect as its input a server-send event heartbeat stream. 9999/hystrix.stream. I have a server-send event heartbeat stream that is always generating new information. As it is, as I say, a heartbeat stream, constantly updating. It's infinite. It has no end. It is without end. It goes on and on and on and on forever and ever and ever. Like the skies and the oceans and the stars and the bugs in your code, just infinite, forever, forever and ever and ever. So whatever you do, and I cannot underscore this enough. Whatever you do, do not curl this endpoint. So I'm going to grab this endpoint here, and I'm going to go to the dashboard that we've just spun up, 8010 hystrix.html. And I'm going to paste that stream that we've just accessed from the circuit breaker, from the node that had the circuit breaker. And let's line things up here. localhost 80, what do we say, 9999 / reservation names. Okay, so I'm making requests on the left. You can see the moving average trending ever upwards on the right. That's 15, 21, 25, 32, et cetera, et cetera, et cetera. Traffic is being made through the circuit breaker from the client to the service, and I can see that reflected here in the output. I can see that there are 0% errors. There's no errors right now. Every request is going through without any problems. The circuit is closed, although if I were to kill the downstream service, the circuit breaker would open. You'd see that reflected here as well. So we have now the ability to see the health of that downstream service because we can look at the circuit breaker. And if I had more than one circuit breaker across more than one instances, I could multiplex that stream into one aggregate stream using Spring Cloud Turbine. But I'll leave that as an exercise for you for later. The point is you could have one user interface, one screen like this with hundreds of circuit breakers being updated live at a time. This is one way to understand the state of the system, to understand the emergent behavior of the system. The last way we're going to look at is distributed tracing. Distributed tracing is very simple in theory. What I want to do is I want to make sure that for every request that enters or exits my system and any node in the system, I want to make sure that I affix a unique correlation ID, an ID by which I can trace or follow the flow of that message through the system. In theory, it's very simple. Just for every ingress and egress point in the application, have some sort of generic logic to track, attach a unique ID, and then perpetuate that unique ID. All the places, right? The feign REST client, the REST template-based REST client, the Zuul microproxy endpoints, the Spring MVC endpoints, Spring Data REST, the Hypermedia REST API, Spring MVC itself, messaging-based microservices with Apache Kafka, or RabbitMQ, or Redis. Anywhere else, anywhere you can imagine data going in and out, you have to add this logic. Simple, except it's not. And it gets really painful if you start to have asynchronous stuff as well. So we have an abstraction for that. We have an abstraction, a library called Spring Cloud Sleuth. Sleuth, like a detective, right? You are one of the few countries that knows that word. And Spring Cloud Sleuth is the abstraction. We have an implementation called Zipkin. And so I'm going to go back to my build here, and I'm going to reinstate that one dependency that we commented out earlier here. Okay. There's this, and then on the client, I'll go here. Do I have Zipkin? Yeah, there it is. Okay. So now Zipkin is an implementation. It is an implementation of that abstraction that works with something called Zipkin. Zipkin is an open source project from Twitter. It's an open source distributed tracing project that released from Twitter in 2010. We at Pivotal are the lead contributors to Zipkin. We sponsor its development these days as well. Well, one of the lead developers, right? Besides Twitter, this is the client-side sort of interface for that. It's the client-side API for that, and it's automatically on the class path. And what it needs is a Zipkin server. So let's go ahead and spin up a Zipkin service here. We'll say Zipkin server, Zipkin UI, config, Eureka, and I think that'll do. Good. So hit go. Okay, here we are. Now on the console of the other services, we should see a lot of blood, right? Because it's going to have a lot of different stack traces as the Zipkin clients are trying to call the Zipkin service, which as yet doesn't exist. So we'll say @enable discovery client, @enable Zipkin server, and we'll spin that up. I'll take some water. Okay. Goody. Localhost 9411. Come on. There we are. So there's our Zipkin server. It isn't aware of any traffic that we've made yet, so let's create some traffic. Okay, there we are. And it still doesn't know about it. Did I have Eureka in here? Did I give it a name? Did it not register? Zipkin here. Client. I think I added it to the class path before IntelliJ had seen the updated dependencies. from Maven. And so it hasn't been broadcasting yet. There we go, that looks better. Yeah, okay, so that yellow there is a telltale sign that it now sees the Zipkin bit, because what's actually happening is that Sleuth is logging information for us already, but we don't care about the logging. Well, what I want to show you is the way it's interacting inside of the Zipkin. Come on. Come on, computer. Where are we? Good. 1. Okay. Give that a second to one started before the other. So it needs to update its own perspective. But in the meantime, half of the equation is involved. This is the reservation service. Come on. Do I want to wait for that 30-second timeout, or do I just want to restart? Reservation service. Okay, there we go. So now, I've made a request. It automatically updated itself. It healed itself as we expect. Now when I go here, I can see both the client and the service are reflected in the console here. If I go to the service, I can see that it knows about the different endpoints that have been invoked. If I click on this, for example, I can see find trace, and I can see that I've made several requests. For example, down here, it shows that I made a request less than a minute ago. If I click on this, it shows that it took 21.9 milliseconds. Click on that, and it'll give me a waterfall graph of the requests that have flown through the system from the very beginning of the exchange, the reservation client, going to the reservation names method, to the names method, to the reservations endpoint, which then lands on the Spring Data REST service, which is served by the Git collection resource endpoint. And if I click on any one of these waterfall graph elements, I see the sort of request log, the in and out, the tags and so on, specific for that HTTP request. And here I can see the host, the method, the path, etc. So this trace information works for anything you can imagine wanting to use inside of the Spring Cloud sort of ecosystem. But of course, it's very easy to add your own. If we want to instrument some sort of exchange or some sort of service that we don't have already, it's very easy to add your own tracer. The default tracer samples 1 out of every 10 requests that it sees flowing through the system. I've got it ratcheted up to 100% because I'm doing a demo. You should not do that, right? If the goal here is to get online telemetry. How much money did we make this last quarter? I have no idea, but I can tell you what the average latency on the website has been for the last hour. That's what this is all about, right? You're not going to sample everything. You don't need to. It's all about seeing online patterns. It's not going to be about warehousing. You're not going to use this for customer service. You're not going to use this to find out what Josh did on the website 2 years ago. Instead, use it to find out what things are doing right now, the emergent patterns. This and the circuit breaker dashboard are ways to do that. And so with this, my friends, we've looked now at how to build systems that are agile, how to build systems that take advantage of the scale of a cloud, how to build systems that do the right thing in the face of service outages and topology changes, and how to build services that are observable, right? Both at the service level and the system level. I wish we had more time to really kind of get into the weeds and look at some stuff. You know, this is a very, very service level sort of skimming of the photo of the actual lake of information, right? So we didn't get to look at a lot of stuff. Maybe next time, maybe we'll cover something in depth. But if we had more time, we'd talk about things like single sign-on and security. How do I protect my different microservices? You can use Spring Cloud Security for that. You can protect services and reject things that don't have a valid OAuth token. If I wanted to do, service cluster management, leadership election, things like that. How do I handle that? That's Spring integration, Spring Cloud Cluster. What if I wanted to handle stream processing, messaging? That would be Spring Cloud Dataflow and Spring Cloud Stream, right? If I wanted to do contracts or consumer-driven contracts to assert that a client and a service share a common contract, I can use Spring Cloud Contract, right? There's a lot of stuff here that we could look at, but we should maybe another time. Now, I hope you liked some of what we looked at here today. I'm certainly a fan, right? I'm wearing the Spring t-shirt and Spring underwear. Of course, I'm a fan, but you don't have to take my word for it. You see, this stuff is being used by lots of small mom-and-pop shops all around the world. Now, geographically, this is a first for me. I've never been in a situation where the following two places are actually west of me, but I have to remember that. So what I was about to say was, in the very, very far west, There's a small company called Netflix that uses Spring Cloud and Spring Boot at scale. They've talked about it, they've spoken about it, they've published articles about it, and so on. Right? They use Spring Boot and Spring Cloud to solve their problems. There's another company called Ticketmaster. They sell tickets, something like $80 to $100 million of tickets every hour go through a Spring Cloud and Spring Boot based system. There's another company, a small company in next door in the West. This is so weird for me. Another company in the West, a small company called Baidu. They're a search engine in China. They serve something like 600 to 800 million search users every day. They have services at production scale that are using Cloud Foundry, Spring Boot, and Spring Cloud. In China, also, there's another small company called Alibaba. They're a mom and pop shop. They're going to be big one day. They're using Spring Boot and Spring Cloud. Have been for years. Well, Spring, but Spring Boot and Spring Cloud more recently, of course. And so, if Amazon.com in the far, far west is the Alibaba of the West, or the far west, then Rakuten.com in the close west is surely the Alibaba of Japan, right? They're using Cloud Foundry, Spring Boot, and Spring Cloud at production scale as well. So for these organizations and many others besides, these organizations have the need to solve these problems. They have the need to solve the motivation to solve these problems. They certainly have the smart people. They could and have, in some cases, solved some of these problems by themselves, but they still chose the pivotal stack because for them, this is the fastest, safest, most productive way to get to production. And that, at the end of the day, is all that matters. So, thank you so much for your time, my friends. I'm sorry we ran a little long. I'm not too sorry. I'm a little sorry, but thank you so much.